Okay, so good morning. So we were looking at uh, Taylor series of two variable function. I think I gave you the formula, but I have not given any proof. So I'll give you a brief proof, which is essentially that. So what Taylor series says that now in case of second variable, if function f of x comma y is, you know, the value at a point a comma b, and its derivatives at point a comma b, then you can find the value of f of xy at any point, right? Any generic point x comma y. So, and also I think so after this Taylor series, what is left is maximum minima, right? For single variable, you remember, you differentiate the function, put it equal to 0, right, and see find the point of inflections, right, and again compute the derivative, and depending on negative or positive, you decide about maximum, minima, and all those kind of things. Similar things exist here. I mean, you can generalize the things to what is known as Hessian matrix. So I think even if I mention it, but I need to give you some idea about positive definite matrix. But are you aware of any matrix idea? Matrix, you know, right? Yeah, but maybe positive definite matrix you don't know, right? You know the eigenvalues? No. So yeah, so I think I'm not going to probably touch that. But yeah, unless you have some more knowledge about matrices, you can look at it. But so anyway, that's something. It's given in the notes if you want. The formula is given, as long as you know what do you mean by positive definite matrix. Anyway, and then important thing is directional derivative. So now in case of single variable calculus, we know that the rate of change can be described by the derivative, right, of the function at that point. So in case of two variable functions, we have different kind of derivatives: partial derivative with respect to x, with respect to y, and so on, right? And the total differential, the idea of total differential, okay, d of z, right? So how do we find directional derivative? So I'll give you an idea about that. How do we define directional derivative? And then eventually this leads to vector calculus, okay, which is kind of very useful for your communication or wireless communication, and all these things, especially this antenna design, all kind of things. Vector calculus is quite useful, right? So I'm not going to do a whole course on vector calculus. There are a lot of references which I can provide to you, but we'll give you the basic idea how this thing evolved, right? So some basic idea about vector calculus, okay, and yeah, so I think that's all. So let us see. I hope we'll be able to cover up to this much today. Okay. So this was the Taylor series for single variable, that f of x is equal to f of a plus f dash of a times x minus a, and so on, where r and x is the remainder in the form of integral, right, and fold integral of that function. So here is the formula for two variable function, right? So f of x comma y is f of a b. You evaluate the function at the point a comma b plus 1 over factorial of 1. Partial derivative with respect to x evaluated at point a b times x minus a plus fy times y minus b. That's the second term. Then third term is all possible derivatives evaluated at point a comma b, fxx, fxy, fyy, right? And then corresponding term involving x minus a and y minus b, right? And then you keep on doing like this, right? So how do we get this formula? So actually, in order to get this formula, we will use Taylor series for single variable. And for doing that, you look at this picture. So this is a point. So this is a region R where the function is defined, right? This function is defined in this region R, right? In a plane, okay? So a comma b is a point, and I say that, okay, that's a starting point, and say x naught comma y naught is a final point. Okay, and x comma y is a generic point. You can vary x comma y along this line, right? You can vary this, right? Now, using this idea, do you think you can write down the equation of the line? A parametric equation of the line you can write easily, right? So I'm going to do that. So AB is the initial point, x naught, y naught is the final point, and x comma y is a generic point. So that means I can write down x is equal to a plus x naught minus a times t. Sorry, x is equal to a plus x naught minus a times t, and y is equal to b plus y naught minus b times t. Clearly these are the parametric equation, right, of the line, because if I put x naught is equal to a, what I am going to get? X equal to a. And if I put y naught is equal to b, so basically when I put the values of x naught, y naught is the point, basically this value we put, we get the first point ab, right, directly. So everything is matching, right? And how do we get it? Because x minus a is multiple of x naught minus a, right, for some t. Similarly, y minus b is multiple of y naught minus b for some t, right? So we can write down these equations, right? Okay. So this is the parametric equation of the line. Now, since we got, so now x can be expressed in terms of t, and y can be expressed in terms of t. I just substitute these values in the f of x comma y, right? So what we are going to get? So basically, in fact, I should say that, yeah, what happens if I put t is equal to 0 here? We get the initial point, and t is equal to 1, we get the final point, right? X naught comma y naught we will get, right? So that's fine. Now I can write down the function f of x comma y is a function for which I want to find the expansion Taylor series. So I can write it down as f of a plus x naught minus a times t and y naught minus b times t. F of x comma y will be, I just substitute the value of x and y. It is like this, right? Now so now a, x naught, a, y naught, b, all these are, okay, 1 minute. B plus, right? All these are constants, right? So the whole thing is function of t only. So I say that, say this is some function of t, right? Some function of t. Okay? So f of x comma y is some function of t. So two variable function is now a function of a single variable t by these transformations, right? Okay? So that means I can apply Taylor series. So this is a function of single variable for t lies between 0 and 1, of course, because t is equal to 0 gives you the first point and t is equal to 1 gives you the end point, right? Okay. So if f is basically sufficiently differentiable, I mean that assumption has to be taken, we can write f of t as f of 0 plus f dash of 0 times t plus f double dash of 0 times t square by factorial 2 plus dot 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 f n minus 1th derivative evaluated at 0 t raised power n minus 1 divided by factorial n minus 1 plus remainder RNT. Agree? Using single variable Taylor series, I have expanded, right? And this is at point t is equal to 0. So basically, right, t is equal to 0, I have written everything, right? You can write down by single variable formula, right, for Taylor series. Any issue here? Now what is left? Just find out these values. What is capital F of 0? Capital F of 0 means what? T is equal to 0. T is equal to 0 means this function will become what? A comma b. So that first term will be f of a comma b, right? As expected. So this term will be f of a comma b because t is equal to 0 will give you the first thing. Now we need to find out something has to be done for this derivative. So let me tell you what we can do. Now this differentiation is with respect to t. F dash of 0 means differentiation with respect to t, because there is only a single parameter t. We are differentiating with respect to t here, right? So I can say that I can use chain rule here now. D over dt, differentiation with respect to t, is nothing but del over del x, dx over dt by chain rule, plus del over del y, dy over dt. I mean, so here it could be some function or whatever it is. So d over dt is, because actually these are functions of x and y also, right? I mean, like those parameters, those are also involved. So partial differentiation with respect to x, dx over dt, plus partial differentiation with respect to y, dy over dt, right? Chain rule. That means, okay, so this I can say that now del over del x basically will what happen, because if you take this quantity, so I denote it by x minus a, x naught minus a times del over del x, because dx over dt, you know what is the value of dy by dt, because x is this, right? X is this and y is, sorry, and y is this, right? So I know what is dx over dt, dy by dt. I can just find out those values. So this is nothing but y naught minus b times del over del y. And I call this whole thing as d, right? Because dx over dt I know, dy over dt I know, right? Because x is that formula, right? So that means what is the value of f dash of 0? Will be d over dt of f of t evaluated at t is equal to 0, right? Sorry, only one differentiation, right? So d over dt of ft at t is equal to 0. This is nothing but d of f of x comma y evaluated at point a comma b, because t is equal to 0 will means point is a comma b, right? So let us compute this. What is this value? So f dash of 0 is nothing but d of f of x comma y evaluated at a comma b. This is nothing but x naught minus a. I am just writing the operator value del over del x plus y naught minus b del over del y. This is the whole operator acting on f. So this is nothing but x naught minus a times del f over del x, which is f of x, plus y naught minus b times f over y, right? Similarly, so this is nothing but d of f, right? I can say that this is d of f, right? And then you need to evaluate it at point a comma b, so the whole thing has to be evaluated at point a comma b, right? So whole thing I can write it down as x naught minus a times f of x evaluated at a comma b plus y naught minus b times f of y evaluated at a comma b. Right, so this is the whole differentiation. F dash of 0 I have calculated, right? Okay, so what is the value of f of 1? F of t is this, right? If you put t is equal to 1, what you are going to get? F of x naught comma y naught, right? So this is f of x naught comma y naught. So simple calculations now basically. Similarly, I think, so Similarly, you can calculate d square f. I'm just writing directly. You can just compute this whole square f of xx plus 2 times x naught minus a, y naught minus b, f of xy plus y naught minus b whole square f of yy. Right. You can similarly compute the double derivative, right? So essentially we have f of x naught minus y naught is equal to f of a comma b, f of 0, capital F of 0 plus 1 over factorial 1 d of f evaluated at a comma b and so on, 1 over factorial n minus 1 d of n minus 1 f evaluated at a comma b plus remainder up to t. So I have used, so I have just computed this value right here. Similarly, you know, second term and so on, you can keep on doing this same thing up till the remainder function is there. Everything is with respect to t. Now in order to get, you know, the whole expression, I need to put t is equal to 1 and then you are, because see, t is equal to 1 gives you the first, you know, that is x naught comma y naught when you put t is equal to 1, right? So you get the f of x naught comma y naught. So we are getting everything at the point x naught comma y naught here, expansion of f of x y, right? You need to put, so here we have done what we have done, we have actually put t is equal to 1. Okay, so t is equal to 1 will give rise to this whole thing, right? T is equal to 1 will give you what? F of t. Here if you put t is equal to 1, so f of 1 is what? F of x naught comma y naught, right? So some calculations, so basically now you have all the derivatives, so whole formula is ready for you actually, right? Got it? So in actually now you see we wanted for a formula for, so here actually you know, everything is coming in terms of x naught comma y naught, because you see that d of f is what? X naught minus a, y naught minus b and so on, right? So x naught, y naught terms, everything is coming, and this side also x naught comma y naught. So just replace x naught by x and y naught by y. You have the whole formula at the way you look like, right? Okay, the way you want, right? So you have the whole formula. Any question? थोड़ा heavy था क्या? So what we have done, we have written the parametric equation of the line, right? So x in terms of t, y in terms of t, just substitute the whole f of x comma y, the two variable function becomes function of t, capital function of t, sum, right? So where if you put t is equal to 0, we get the first point, t is equal to 1, we get the end point, x naught comma y naught, right? Then we use the formula for single variable and apply everything, you just open, right? Using single variable. Now where the differentiation is with respect to t, so we need to take care of the derivative, right? Differentiation with respect to t, so we use chain rule to find out in terms of x and y. We substituted those values, we computed d, I mean that capital D kind of thing, right? So we just f dash of 0 is what, and so on and so forth, you can just find out everything. And so we have got the whole series expansion, right? So the way you want it, right? It's not very difficult. Yeah, so I think maximum and minimum I am skipping right now, but because it involves some more things. Okay, I think now we are ready for directional derivative thing, okay? So what do you mean by directional derivative? So when we are actually differentiating, right? So if f of x comma y is a two variable function, we differentiate partially with respect to x, so we are differentiating in the direction of x. Similarly, we are differentiating in the direction of y, right? So partial derivative with respect to y, right? But if we want to find derivative in any direction, how do we find? Okay, because now you know it's a surface, right? In single variable case, you know it was just a graph, right? Some curve, okay? So if u is equal to a comma b, I mean a comma b is an arbitrary unit vector, we can define what is called as a directional derivative of f at a point x naught comma y naught in the direction of a unit vector a comma b, right? U is equal to a comma b, and we denote it by d of u f of x naught comma y naught. So again we are using the definition as usual. You can see that limit h tends to 0, f of x naught plus ha comma y naught plus hb minus f of x naught comma y naught divided by h. This is the usual definition of the derivative, right? Simple. Now how do we compute this? That I am going to simplify for you. Okay, this formula. Okay, so this is limit h tends to 0, f of x naught plus ha comma y naught plus hb minus f of x naught y naught. This is the usual formula, right? If this limit exists, we say that the directional derivative exists in the direction of the unit vector u, which is a comma b, right? So in order to understand this, now you see that I am taking this picture. Look at the picture here. So this formula is important. Now we need to understand this formula, right? That what is happening here. So let me actually write it down. So basically we have z is equal to f of x comma y. This is a two variable function, so basically it's a surface, right? Some surface, fine. So f of x represents rate of change of f in the direction of I. I is the unit vector. You remember I is the unit vector. Similarly, f of y represents rate of change of f in the direction of j, right? Unit vector j, right? Differentiation of x, so rate of change in the x direction, x-axis direction, rate of change in the y-axis direction. So our question is how to find rate of change in any direction. That is our question. Okay. So z is equal to f of x y is a function. So basically it's a surface. So now f of x naught comma y naught is limit h tends to 0, f of x naught plus h comma y naught minus f of x naught comma y naught divided by h. This formula is familiar to you. Partial differentiation with respect to x, right? So this is the rate of change in the direction of x-axis, right? In the direction of the unit vector I. Similarly, we can find h tends to 0, f of x naught comma y naught plus h minus f of x naught y naught divided by h. Okay. So let me now basically this is derivative in x-axis along x-axis, this is y-axis, right? I want to now define differentiation of f of x naught comma y naught. So at a point x naught y naught we want to find the differentiation along a unit vector u. So u is a vector a comma b. So it's an arbitrary unit vector actually. So I think you can see that if we put u is equal to I, this is 1 comma 0, j is equal to 0 comma 1, right? Right? Unit vector. So component, we are writing the, both the components, right? So this value is nothing but limit h tends to 0, f of x naught plus ha, y naught plus hb, minus f of x naught comma y naught divided by h. So we are saying that now if you want to find the rate of change along any unit vector, so we know along I axis, along j, along any unit vector u, the derivative is defined as limit h tends to 0, x naught plus ha, y naught plus hb. Okay, so let me see the geometrical significance, then you will understand it better. So if this limit exists, right, so we can do everything. Now let us see here. Now look at this picture here. This is what? This bigger thing. You can think like it as a watermelon, right? Surface of a watermelon, right? Now, चाकू देखा है ना बड़ा वाला, तो अगर हम ये चाकू काट रहे हैं, देखो इसको, है तो क्या करेगा ये चाकू? क्या करेगा? इसको एक कर्व पे कट करेगा ना, ये कर्व सी, राइट? एक बड़ा सा वाटरमेलन लिया और चाकू से काटेंगे तो somewhere it will curve, it will intersect in a curve, right? That's what I'm saying, right? So this is a curve. Okay, so basically in mathematical terms we say that this is the surface and then there is a plane which is intersecting in a curve, right? तरबूज और चाकू तो तुमको समझने के लिए ना आम भाषा में. Okay, fine. So now what happens on this? So basically this curve C, there are 2 points. So one point is this P, and which is x naught, y naught and z naught, because this is 3-dimensional thing, right? X, right? So that point is x naught, y naught, z naught. And suppose there is another point Q. See, now actually I am going to compute the derivative in this direction of this line. So there is another point Q here, which is x, y, z, and just like that we were finding the tangent on a curve in a single variable calculus, right? You take 2 arbitrary points and make them as close as possible, right? Similar thing we are doing here, but now here is a surface, right? So we look at this curve C here, then what you do, I basically I will make closer these 2 points P and Q and see what happens, right? So basically I drop, what I can do on this plane, I can actually get these lines here intersecting at this point and this point, right? So this is kind of projection, right? So here the z component is 0 in this plane, right? You have P prime x naught y naught 0, Q prime x y 0, right? Clear? मुश्किल है, थोड़ा देखने की बात है क्या हो रहा है, right? So what we have done, we have a surface, there is a tangent, not tangent, plane, intersecting in a curve, right? That curve is C, right? And in that curve I have taken 2 arbitrary points P and Q. P is this point. Since this is a surface, so actually this is 3-dimensional, right? So we have point R x naught, y naught and z naught. Okay, and this is another point x, y, z. Now I will play with these points, but before that what I am going to do, I project them on the plane. So this point will be x naught, y naught 0. That z component will be 0 here, right? Similarly the other point x, y 0, right? Now distance between this and this is h. So remember in that limit business, h used to be the length of, right, which you want to minimize, right? Okay, that point is h. So basically if h approaches towards 0, this point and this point will move towards each other, right? And in that case P and Q will move along the curve at the same time, right? That will happen, right? And so basically now what we want in this direction, so if I actually draw a tangent here at this point P, this tangent represents basically the derivative in the direction of the unit vector u, because this vector is here, you know, this is the unit vector u in this direction, right? Okay, got it? On the xy plane, this is the unit vector u, right? And this actually, this one and this tangent are parallel, right? So basically they will, I mean, they're in the same direction, right? Okay, so this is the whole thing, right? Any question about this picture now? I hope it is clear. So there is x-axis, y-axis, the plane. When we plot the surface, it will be a surface kind of thing. Okay, तरबूज समझ सकते हो? उसको हमने एक चाकू रखा, जिस डायरेक्शन में हमको डायरेक्शन डेरिवेटिव निकालना है actually, right? So basically, this will intersect in a curve. I can take two arbitrary points P and Q on the curve, right? Sufficiently close means the distance is h between them, right? Here, corresponding projections will have distance h, right? Any question in this picture? It's clear, right? Now, so the vertical plane that passes through P in the direction of u intersects S on a curve C. The slope of the tangent line T to C is at point P is the rate of change of Z in the direction of u. That is what it's saying. So basically, that tangent T, capital T, which I have written at the point P, is rate of change of the function in the direction of u. U is a arbitrary unit vector, right? Okay, so now we are ready. So from these calculations, what I can do here, now can I say that x minus x naught, so you can see that P prime Q prime, P prime Q prime is what? This thing, right? P prime Q prime is h time u, unit vector, for some h. Is it clear, right? So P prime Q prime is some scalar time unit vector u, right? Scale ka difference hai bas, right? That h. So that means, and I know u is a unit vector with component a comma b, so I can expand it. So this will be HA comma HB, right? So basically line P prime Q prime is parallel to U. Since line P prime Q prime is parallel to U, we have this quantity, and then from here I can find out. Now basically this means that what is x minus x naught is h times A, and y minus y naught is h times B, because of that parallel condition, right? So what I'm saying, that x minus x naught is h time A, and y minus y naught is h time B. From this picture it is clear, right? That means now we have got this value which I can use. So rate of change of Z, I want to compute this limit actually, is nothing but Z minus Z naught divided by H, which is nothing but f of x naught plus HA comma y naught plus HB minus f of x naught y naught divided by h. I've just substituted the value because z is what? F of x comma y, right? Which I have substituted here, and then I have used this value that x minus x naught is equal to HA. So x is equal to x naught plus HA. Similarly, since y minus y naught is equal to HB, so y is equal to y naught plus HB. I have substituted those values here, minus this, right? So yeah, here. So basically we get this formula, right? So directional derivative of f of x naught y naught at the point x naught y naught in the direction u is this limit as s tends to 0. Okay, so this is the formula that we got. How we got this formula, right? I mean, right? So this is nothing but the rate of change of the two variable function in the direction of a unit vector u. शायद तुमको एक बार दोबारा पढ़ना पड़ेगा, right? I think शायद मेरे को लग रहा है कि शायद थोड़ा disconnect है, right? So पढ़ लेना, right? No issue. It's not very difficult, but I think again it's just that picture, right? हमने क्या किया है? I have to find derivative of the. So we know, again I'll just 2 minutes में दोबारा recall कर देता हूँ what we have done. Z is equal to x f of x comma y is a two variable function. I can plot it as a surface, right? Here for the simply understanding I have taken it as a जैसे तरबूज होता है, right? Now this is a surface, right? Then I put a, now I want to find, so I know the derivative of f in along the unit vector I, which is along the x-axis, along the unit vector y, right? Along the unit vector j, along the y-axis, right? That I know the formula. I want to find the formula in any direction of the unit vector u, in any direction, right? So उस direction में हमने चाकू रखा, उसने तरबूज को काटा एक कर्व में, right? जहाँ पे काटेगा ना वहाँ पे वो कर्व C है, C पे हमने 2 पॉइंट लिए P and Q. चूंकि 3 डायमेंशन है तो उसके पैरामीटर्स क्या मतलब वैल्यूज क्या होंगे, x नॉट y नॉट z नॉट एंड x y z. उन पॉइंट्स को हम आपस में क्लोज करेंगे, राइट? जैसे करते हैं, ठीक है? इनका प्रोजेक्शन किया प्लेन के ऊपर तो एक हमें पॉइंट मिला x नॉट y नॉट 0 और दूसरा मतलब p प्राइम विच इज x नॉट y नॉट 0, दूसरा क्या मिला x y 0, राइट? एंड दिस पॉइंट, सो बेसिकली नाउ इफ यू ड्रॉ ए टेंजेंट एट p along that curve C, right? So that tangent actually will be parallel to the in that same direction, right? Where you want to find the derivative. So if you go to the xy plane, that results into the yeah, I can again show you the picture, right? So so you know this line is actually in the same direction in the unit vector u, right? And from here I know that if I make these, and h is the distance between them, basically this is parallel, right? Because the line p prime q prime is parallel to the unit vector u in that direction, right? So that means p prime q prime is h times u for some scalar h here. This is the h, okay? And so we have hb, that means x minus x naught is equal to h times a, which you can find from here also. X minus x naught is h times a, y minus y naught is h times b, right? Now what I have done, simply apply the formula, the rate of change of z. So delta z divided by h. I have to compute delta z divided by h. That's all. So if I compute this quantity as limit s tends to 0, we will find the derivative, right? Z is a function of x comma y. Delta z will be what? Now z minus z naught divided by h. Z is equal to f of x comma y. So f of x minus y minus f of x naught comma y naught. X और y की वैल्यू हमको पता लग गई है, which is x naught plus ha, y naught plus hb. So here is the formula. Right? Got it? कुछ लोग अभी भी खोए हुए हैं, right? I can see that, but okay. तो फिर एक बार और तुमको चाय लेकर के बैठना, right? You will get it, right? So okay. So it's not very. So basically, the directional derivative you can compute in any direction. That is very, very important now, right? So essentially, you require this formula only, right? So I gave you that idea how this formula is coming up, right? This formula, you know now. So actually in this formula, if you take u to be 1, 0, which is the I, what will happen? So this will be nothing but d of I of f of x naught comma y naught is nothing but f of x. Similarly, you can get f of y, right? When you take j vector. If u is I, you get derivative with respect to x. If u is j, you get derivative with respect to y. Now I think there is a nice theorem which I would like to prove also for you, because the proof is not difficult. Oh, so आज ज़्यादा time निकल गया. Anyway, no problem. If f is a differentiable function of x and y, then f has a directional derivative. I call it dd. क्यों लिखे पूरा ना? Directional derivative dd in the direction of direction, short form देखो, direction drn, right, of any unit vector. Vr means vector, okay. बाद में ये मत समझना ये कहाँ से लिखा है ये सब, right. u is equal to a comma b. So basically then f has a directional derivative, and this value is given by d of u f of x comma y is equal to f of x a plus f of y. So वो तो हमने लिमिट देखा था. Now actually this is the actual expression, and we are going to use that. लिमिट कौन बार बार यूज करता है, right? We are going to use this formula for finding the directional derivative. So how do we prove it? I think we have 5 minutes to prove this. Okay. So what we do here, we define g to be a single variable function of h as f of x naught plus ha y naught plus hb. So basically what I am doing, f of x comma y was the two variable function. Substitute x equal to x naught plus ha and y is equal to y naught plus hb, and this whole thing is a function of h. I am calling it g of h. Okay. So then what will the value of g dash of 0? Will be limit h tends to 0, g of h minus g of 0 divided by h. This is nothing but limit h tends to 0, f of x naught plus ha comma y naught plus hb minus f of x naught comma y naught divided by h. Right? So whole thing is written like g dash of 0. Okay? That is fairly simple. Then, so in other words, what I am saying that g dash of 0 is nothing but directional derivative of f of directional derivative in the direction of u of f of x naught comma y naught. Right? Right, by definition, right? So g dash of this is nothing but the directional derivative of f of f at the point x naught y naught in the direction of u, right? Which is nothing but g dash of 0. बस अब 1 minute लगेगा and we can prove it finally, right? So now g of h is what? F of x comma y, right? This is what it was, right? I have just substituted the value of x comma y there, right? If you remember. So we have x is nothing but x naught plus ha and y is nothing but y naught plus hb. These things we know. So by chain rule, g dash of h is nothing but del f over del x dx over dh plus del f over del y dy over dh, which is nothing but f of x, and dx over dh is nothing but what? A, and dy over dh is nothing but b. So this whole thing is this times a plus fy times b. Right. So actually we wanted to find g dash of 0, which is nothing but f of x evaluated at x naught y naught times a plus fy x naught y naught times b. As you know, for h is equal to 0, x is equal to x naught and y is equal to y naught. Right. So this is the formula. Right. Okay. So now if I have to compute directional derivative in any direction, just compute partial derivative. Right. And then we use this component a and b in whatever direction you want in that vector, right? And this will give you the value. The whole thing can be written as dot product of two vectors, right? So vector calculus का जन्म हो जाएगा यहाँ से, right? Okay. So now you can deal everything in terms of vector calculus, right? So which I'll tell you about. So basically, direction derivative of a two-variable function give rise to a vector calculus thing, right? So now you have dot product of two vectors, because this is nothing but a u is equal to a comma b, and the dot product is, so basically del of f of x and f of y. Take that vector dot with u, you give the directional derivative in that direction, right? So I'll give you some more examples and maybe again some of these things in, when is the next class? इस वीक में है ना, खत्म हो गई?